Right now, 22,000 miles above your head, there is a satellite staring down at the cold, dark expanse of the Earth.
Just, silently waiting for a flashlight to turn on.
Exactly. And if that flashlight flashes in the wrong part of the world, well, a 20-minute countdown to the end of human civilization basically begins.
Which is a terrifying thought, but it's the reality of what we're looking at today.
It really is. We are talking about an invisible shield made of mathematics, infrared light, and radar waves that operates silently every single second of every day. Welcome to the Doctrine Deep Dive.
We have an incredibly high-stakes mission for this deep dive.
We do. We are exploring the cutting-edge, frankly mind-bending world of space operations, focusing entirely on how the military detects, tracks, and defends against incoming missile threats.
And, the scale of what we are analyzing today really defies standard human comprehension.
Well, completely.
We are discussing objects traveling at 20,000 miles per hour, sensors that are parked a tenth of the way to the moon, and automated systems that have to calculate global trajectories in fractions of a second.
To really ground this discussion, we are pulling directly from the foundational doctrine.
Right, the heavy reading.
The heavy reading. Specifically, the United States Army Space Reference Text for 2026, the Joint Publication 3-14 on Joint Space Operations, and the Space Doctrine Publication 3-103 on Missile Warning and Tracking.
And our goal here is to strip away the jargon, to really get to the underlying physics and the strategic logic of these systems.
Because here's why this matters to you, the listener.
Yeah.
We live in an era where adversary capabilities are evolving at an alarming pace.
Yeah, the distances these weapons can cover are staggering, and the time we have to react is just continuously shrinking.
So understanding the architecture that protects the homeland and deployed forces is critical for any serious student of military strategy.
Absolutely.
But before we can understand how the United States builds a warning architecture to look for a threat, we first have to establish, well, the physical nature of the threat itself.
Right, you have to know what you're looking for. The doctrine actually spends significant time breaking down the technological state of these weapons.
So at the foundational level, what really separates a missile from, say, just a really big artillery shell?
It basically comes down to sustained internal propulsion and the ability to carry a distinct package over vast distances.
Okay, so it's not just the initial boom of a cannon pushing it.
Exactly. Anatomy-wise, a missile consists of two primary components. The first is the rocket booster. This is the propulsion system.
The part with the fire.
Right, the fire. It is essentially a giant controlled explosion directed downward to create just an enormous amount of thrust.
The sheer thermal output required to lift tens of thousands of pounds of metal and fuel off the Earth's surface against the pull of gravity is immense.
It's massive. And the second component is the weaponized payload. This is the actual munition, which is housed inside the vehicle.
And depending on the intent, that payload could be conventional high explosives or chemical or biological agents.
Or, nuclear warheads.
Right. And the propulsion system really dictates the entire classification of the weapon. The doctrine starts with the most traditional category, which is the ballistic missile.
Yeah, and the term ballistic implies a very specific relationship with gravity and momentum.
Like if I throw a baseball into the air, the moment it leaves my hand, I'm no longer imparting energy to it.
Exactly. The rest of its flight is governed purely by the initial force you applied, gravity pulling it down, and the air resistance pushing against it.
And that physical principle just scales up directly to a ballistic missile, right?
It does. A ballistic missile uses its rocket booster for only a very short fraction of its total flight. This is what we call the boost phase.
So the engine ignites, the missile accelerates violently upward, and then relatively quickly the fuel is exhausted and the engine cuts off.
And from that specific moment forward, the missile is just coasting. It follows a highly predictable, unpowered, parabolic trajectory.
It exits the dense parts of the Earth's atmosphere, travels through the vacuum of space during its mid-course phase, and then
gravity pulls it back down into the atmosphere during its terminal phase.
Right.
Yeah.
And because it operates on that predictable parabolic arch,
Right.
if sensors can pinpoint exactly where it started and measure its velocity at the exact moment the engine cuts off, the math tells you exactly where it's going to land.
Yeah, it is a terrifyingly large physics equation, but it is a solvable one.
And the text categorizes these ballistic threats
Yeah.
purely by the distance they can cover, don't they?
Yes. We start with short-range ballistic missiles, which travel less than 1,000 kilometers.
Okay, what's next?
Then we move to medium-range ballistic missiles, reaching between 1,000 and 3,000 kilometers.
Getting bigger.
Oh, yeah. Above that are intermediate-range ballistic missiles covering between 3,000 and 5,500 kilometers.
And finally, the big one.
Right, the ultimate strategic threat, intercontinental ballistic missiles, which travel further than 5,500 kilometers. They can cross oceans.
Now, the predictability of that ballistic arch is what allows defensive systems to calculate where the payload is heading.
Exactly. But adversaries obviously understand our reliance on that physics-based predictability.
Right, which has driven the development of the second major category detailed in the doctrine, which are non-ballistic missiles.
Yes, and these systems are engineered explicitly to break those mathematical models we just discussed.
The primary examples given are cruise missiles and hypersonic glide vehicles.
Let's talk about cruise missiles first. A cruise missile seems functionally closer to an aircraft than a traditional space-reaching rocket.
How so?
Well, it uses a small booster to get off the ground, but then it ignites a jet engine and flies entirely within the Earth's atmosphere.
So it's basically like an unmanned drone?
Pretty much. It has aerodynamic surfaces, meaning it can maneuver, change direction, and fly incredibly low to the ground.
To hide behind the curvature of the Earth, I assume. Or use mountains and valleys to mask its approach from radar.
Exactly. The atmospheric flight profile of a cruise missile is a massive challenge for early warning systems.
Because traditional radars are looking up, right? Scanning the high atmosphere in space for those massive ballistic arches.
Right, while a cruise missile hugs the terrain, staying beneath the radar horizon for as long as possible.
But the technological leap that the doctrine highlights with the most urgency is the hypersonic glide vehicle.
Oh, absolutely. This system combines the high-altitude launch of a ballistic missile with the maneuverability of an aircraft.
I want to break down the mechanics of the hypersonic glide vehicle because the physical forces involved seem completely paradoxical to me.
They are wild.
It uses a massive rocket booster to get high into the atmosphere, traveling at, in excess of 5 times the speed of sound.
Right, Mach 5 or faster.
But instead of continuing into the vacuum of space on a predictable arch, the payload detaches and begins gliding back down into the denser layers of the atmosphere at those extreme speeds.
Yeah, and the question is, how does an object travel that fast in the atmosphere without burning up or tearing itself apart when it tries to turn?
Exactly. How does it do that?
Well, that is the engineering marvel and the terror of the system. The friction generated by moving through the atmosphere at hypersonic speeds is so intense that the air molecules in front of the vehicle literally break apart.
Wait, really? It breaks the air?
Yes, creating a sheath of superheated plasma around the vehicle. The vehicle has to be built with advanced thermal protection systems just to survive its own speed.
But the critical factor is its aerodynamic shape, right?
Right. Unlike a blunt ballistic warhead, a hypersonic glide vehicle has a lifting body. It uses the very atmosphere that is trying to burn it up to generate lift.
So it can essentially skip off the denser layers of the atmosphere or pull into steep banking turns.
Yes, so the trajectory changes mid-flight. Our mathematical model based on the initial launch trajectory is rendered completely useless the moment that vehicle decides to bank left.
That's terrifying. The impact point could shift by thousands of miles after the boost phase has ended.
Exactly. You simply cannot plot a parabolic arch for an object that is flying under intelligent control.
And the doctrine introduces one final wild card that takes unpredictability to its absolute limit, the fractional orbital bombardment system.
Yes, the fractional orbital bombardment system. It sounds like a relic of the Cold War, yet the text presents it as a highly relevant modern threat.
So the concept is that an adversary mounts a weaponized payload onto a massive rocket.
But instead of aiming for a parabolic arch that eventually hits the ground, they launch the payload entirely into low Earth orbit.
So the weapon actually becomes a satellite that circles the globe.
Right. But the fractional part of the name means the adversary initiates a retrograde burn-firing thrusters against the direction of travel to slow the payload down,
causing it to drop out of orbit and strike a target before it completes a single full revolution around the Earth.
The strategic advantage of placing a weapon into orbit, even temporarily, is the destruction of geographic predictability.
Because during the Cold War, the United States built massive radar installations facing north over the Arctic, right?
Exactly. Because physics dictated that the shortest distance for an intercontinental ballistic missile traveling from the Soviet Union to North America was right over the North Pole.
But a fractional orbital bombardment system just ignores that geography.
Completely. An adversary could launch a payload south, let it cross Antarctica, and bring it up through the southern hemisphere, approaching the United States from a direction where we have historically had vastly less radar coverage.
And the ultimate target remains totally unknown until the moment the retrograde thrusters fire and the vehicle drops from orbit.
Yep, it's the ultimate sneak attack from space.
Okay, so if non-ballistic missiles, like hypersonic glide vehicles, can steer unpredictably at Mach 5, and fractional orbital bombardment systems can drop from orbit from literally any direction,
I know where you're going with this.
it seems like our entire physics-based warning architecture is obsolete. If the math no longer tells us where the payload is going to land, the entire concept of early warning seems compromised.
It's a fair point. The maneuverability of the payload drastically complicates the defense, but it does not render the warning architecture obsolete.
How so?
Because the fundamental flaw in maneuverable payloads is that they still require an initial energy source to escape the Earth's gravity.
Oh, right.
Whether you are launching a highly predictable ballistic missile or an incredibly complex fractional orbital bombardment system, you have to ignite an enormous rocket booster on the surface of the Earth.
And that ignition is a physics problem the adversary just cannot hide.
Absolutely cannot hide. The heat signature of a rocket booster pushing through the lower atmosphere is monstrous.
It creates an infrared plume that is intensely bright against the thermal background of the Earth.
Right. And our sensors are designed to detect that specific thermal event the exact moment it happens, so the initial warning remains intact.
The system still detects who fired the weapon and exactly when they fired it.
What maneuverable payloads do is violently compress the timeline for everything that happens after the launch.
Ah, I see. So the warning architecture knows a threat is airborne, but the defense just has vastly less time to calculate the final destination before the weapon arrives.
Exactly. That distinction fundamentally changes the psychology of the operations centers receiving these alerts.
Okay, so we understand the physical nature of the threats, from predictable arches to atmospheric skipping.
Right.
The next logical step outlined in the doctrine is understanding who the military is actually warning when a launch is detected.
Because the audience dictates the threshold for sounding the alarm. And the doctrine divides this into two completely distinct operational domains.
Strategic missile warning and theater missile warning. Let's start with strategic.
Strategic missile warning is the highest echelon of threat detection. The focus here is exclusively on the survival of the homeland and the continuation of government.
So the users of strategic warning data are the President of the United States, the Secretary of Defense, and the commanders at the North American Aerospace Defense Command.
Right. They are primarily concerned with intercontinental ballistic missiles, potentially carrying nuclear warheads aimed directly at North America or allied nations.
And because the stakes are the potential annihilation of cities and the triggering of a retaliatory global nuclear strike, the margin for error must be zero.
It has to be zero, which is why the doctrine mandates a concept called dual phenomenology to ensure that a false alarm never reaches the president.
Dual phenomenology. Break that down for us.
It's a fascinating study in building technological safeguards against human and systemic error.
Okay.
The doctrine states that to declare a strategic threat valid, the warning must be independently verified by two completely different types of sensor systems relying on completely different laws of physics.
So usually, this means an initial detection by a space-based sensor looking for the infrared heat of the launch, followed by a completely separate ground-based radar system physically tracking the solid metal body of the missile as it rises over the horizon.
You've got it. It has to be seen by two completely different methods.
To put this into historical context, the necessity of dual phenomenology is basically written in the blood of near misses, right?
Oh, absolutely. Think back to 1983. A Soviet officer named Stanislav Petrov was sitting in a warning bunker near Moscow.
This is a wild story.
It really is. The Soviet early warning satellite system, which relied solely on infrared detection, suddenly reported 5 American intercontinental ballistic missiles inbound.
The alarms are blaring. The protocol demanded an immediate nuclear retaliation.
Right, but Petrov noticed the ground-based radars were completely silent. They saw nothing.
He gambled his life on the theory that the satellite was glitching, and he refused to pass the warning up the chain of command.
And he was right. The satellite had detected sunlight reflecting off high-altitude clouds at a very specific angle, and it interpreted that intense glare as rocket plumes.
That historical event perfectly illustrates the vulnerability of relying on a single phenomenology.
A sensor anomaly, a solar reflection, or a software glitch can easily create a phantom launch on a screen.
But sunlight reflecting off a cloud does not bounce radar waves back to a receiver.
Exactly. By demanding that a ground-based radar confirm the physical presence of an object on the trajectory predicted by the space-based heat sensor, the architecture mathematically eliminates the possibility of a single-system false alarm triggering World War III.
Okay, but the moment we pivot from strategic missile warning to theater missile warning, the rules completely invert, don't they?
They do. Theater warning is focused on deployed forces, combatant commanders in active war zones, and regional allies.
Because the threats here are not intercontinental. They are short-range and medium-range ballistic missiles.
And in a theater of operations, the luxury of time just evaporates.
Right. An intercontinental ballistic missile might take 30 minutes to reach its target, providing a window to wait for radar confirmation.
But a short-range ballistic missile might have a total flight time of 3 or 4 minutes.
Wow.
3 minutes.
Yeah. If an operations center waits for a secondary radar system to confirm the track, the missile will have already detonated over the base.
Therefore, the doctrine explicitly replaces dual phenomenology with the principle of assured warning.
Exactly. Assured warning means the moment a space-based sensor detects an infrared launch signature that algorithmic models suggest is a short-range threat, the alert is pushed instantly to the troops on the ground without waiting for any secondary confirmation.
So the operational psychology shifts entirely. In strategic warning, a false alarm is the worst possible outcome because it could start a nuclear war.
But in theater warning, a missed alert is the worst possible outcome because troops die, right? Waking up a battalion of soldiers in the middle of the night to dive into concrete bunkers or equip chemical protective gear because a satellite misinterpreted a distant industrial explosion as a missile launch. Well, that's an acceptable disruption.
It is. Failing to sound the siren because you are waiting for absolute certainty is a catastrophic failure of command. A false alarm is just an accepted, baked-in operational risk to ensure survival.
But this places an immense burden on the automated system.
Oh, massive burden.
If a massive infrared bloom registers on a satellite, the computers have to decide in a matter of seconds whether this requires the slow, methodical verification of dual phenomenology because it looks like a threat to Washington, D.C.
Or the instant, unverified alert of assured warning because it looks like a threat to a forward operating base in Europe.
How does it do that so fast?
The categorization happens almost instantaneously through complex trajectory analysis. The space-based sensors are not just taking a single photograph, they are capturing continuous data.
So within seconds of the initial heat detection, advanced computing architectures are analyzing the angle of ascent, the intensity of the thermal bloom, and the acceleration rate of the booster.
Right. If the burn profile is massive and sustained, suggesting the energy required to throw a payload across an ocean, the system flags it for the strategic track.
But if the burn is short and steep, consistent with a regional strike, the alert is immediately pushed down into the theater event system to sound the alarms on the ground.
Exactly. It's incredibly smart and incredibly fast.
So we have established the physical threats and the differing rules of engagement for strategic versus theater audiences.
Which brings us to the physical hardware that actually performs these detections.
Right. The next critical phase of the doctrine details what the text calls the tandem sensor architecture.
The word tandem implies a relay race, a coordinated handoff between two distinct environments. Let's start with the high ground, the space-based sensors, which the doctrine refers to as the first look.
Satellites. They provide the persistent global coverage that makes early warning possible in the first place.
Yeah, they operate far above the Earth's atmosphere, just staring down at the surface continuously.
The doctrine highlights older systems like the Defense Support Program and the modern space-based infrared system.
And the placement of these satellites is critical to their function. They don't just float randomly, they are parked in highly specific orbital regimes.
The primary regime mentioned is geosynchronous Earth orbit.
Right, which is roughly 22,000 miles above the equator.
And at that exact altitude, the speed required for a satellite to stay in orbit perfectly matches the rotational speed of the Earth.
Yes, so from the perspective of someone on the ground, the satellite appears completely stationary in the sky.
That allows a single sensor to constantly stare at an entire hemisphere without ever moving out of position.
It provides incredible wide area persistence, but it has a geometric vulnerability.
Because the satellite is positioned over the equator, its viewing angle toward the extreme northern and southern polar regions is very shallow, right?
Exactly. It's difficult to look over the horizon of the curve of the Earth from the equator to see a launch happening near the North Pole.
So to solve this, the architecture relies on a second orbital regime, the highly elliptical orbits.
Yes. These are often referred to as Molniya orbits, tracing back to early Soviet communications satellites.
A satellite in a highly elliptical orbit does not stay stationary.
No, its path is stretched out into a massive oval. It swoops down relatively close to the Earth over the southern hemisphere, traveling incredibly fast, and then flings way out into deep space over the northern hemisphere.
Oh, so as it reaches the furthest point of its orbit, the apogee, it slows down dramatically?
Exactly, allowing it to hang or linger over the northern polar regions for hours at a time, staring directly down at the Arctic.
So between the equatorial stare of geosynchronous orbits and the polar linger of highly elliptical orbits, the Earth is constantly observed.
And what they are observing is thermal contrast.
Because the surface of the Earth, even a hot desert, is relatively cold from the perspective of space.
Right. When a ballistic missile launches, the rocket booster generates thousands of degrees of heat. The infrared sensors on these satellites are designed to detect that specific wavelength of thermal energy.
Against the cold background of the planet, the exhaust plume of a missile looks like a brilliantly bright beacon turning on in a dark room.
The space-based sensor registers the beacon. It records the precise geographical coordinates of the launch and begins tracking the initial trajectory.
But a ballistic missile does not burn its engine all the way to the target. The boost phase ends.
Right. The fuel is exhausted, the engine cuts off, and the massive thermal plume just disappears.
And at that exact moment, the missile enters the mid-course phase, coasting silently through the vacuum of space. And the space-based infrared sensor becomes practically blind.
The heat is gone, leaving only a cold piece of metal traveling at immense speed.
This is where the tandem nature of the architecture executes the handoff. The first look from space transitions to the follow-up from terrestrial-based sensors.
We are shifting from infrared detection to electromagnetic radar tracking.
Now, when we talk about these terrestrial radars, it is vital to shed the mental image of a spinning metal dish at a local airport.
Oh, absolutely. The ground-based radars detailed in the doctrine are monumental pieces of engineering. We are talking about massive building-sized structures.
The text specifically calls out the upgraded early warning radars strategically positioned around the northern hemisphere.
There is an installation at Thule in Greenland, another at Fylingdales in the United Kingdom, and one at Clear in Alaska.
Looking at their geographic placement, you can really see the legacy of the Cold War strategy.
Yeah, these radars basically form an electronic wall looking northward over the Arctic, scanning the most direct routes between the Eurasian landmass and North America.
The doctrine also highlights the Perimeter Acquisition Radar Attack Characterization System in North Dakota, which scans the northern interior of the continent, and the Cobra Dane radar in the Aleutian Islands of Alaska, monitoring the western Pacific corridors.
And these facilities utilize phased array technology, which fundamentally changes how a radar tracks a target.
Because a traditional dish radar has to physically rotate its antenna to sweep the sky, right?
Right. And if an intercontinental ballistic missile is moving at 15,000 miles per hour, by the time a mechanical dish rotates back to the same spot, the missile has traveled miles.
But a phased array radar has no large moving parts.
None. The face of the building is covered in thousands of tiny, individual transmit and receive modules.
So by slightly altering the timing or the phase of the electromagnetic waves emitted by each individual module, the radar can electronically steer the combined beam of energy through the sky at the speed of light.
It's amazing. It can emit a pulse, bounce it off the cold metal body of the coasting missile in space, receive the reflection, and then instantly steer a new beam to a completely different part of the sky to track a second object, all within a fraction of a second.
So a phased array radar can simultaneously track thousands of objects, decoys, debris, and actual warheads without ever physically moving.
Exactly. It calculates the exact velocity, trajectory, and radar cross-section of the cold objects, feeding that data into the predictive algorithms to pinpoint the final impact point.
To visualize this tandem effort, consider how a high-speed pursuit works. The space-based infrared sensors act like a police helicopter hovering high above a city.
Okay, I like this analogy.
They see a vehicle aggressively accelerate out of an alleyway, their thermal cameras picking up the heat of the tires and the engine block. They instantly transmit the exact starting location and the initial heading of the vehicle.
But once that vehicle enters a long, dark tunnel, the helicopter loses visual contact.
Right. The helicopter relays the trajectory data to ground units waiting at the other end of the tunnel.
And those ground units, equipped with precise speed tracking equipment, take over the moment the vehicle emerges.
The terrestrial-based phased array radars are those ground units.
They receive the initial vector from the satellites, focus their electronic beams on the predicted corridor of space, and acquire the cold missile the moment it rises over the radar horizon.
The speed at which this data must be shared is staggering.
Oh, yeah. The satellite's 22,000 miles in space and the massive radars in Greenland are not operating in isolation.
They are continuously feeding their raw data into processing hubs. The doctrine highlights the Joint Tactical Ground Station as a critical node in this network.
The Joint Tactical Ground Station serves as the processing brain for the theater commander.
It receives direct downlink data from the infrared satellites, processes the thermal signatures, correlates that information with available terrestrial radar tracks,
and rapidly pushes early warning alerts across the data networks to the operational units on the ground.
It is the vital translation mechanism that turns raw physics data, a thermal bloom or radar return, into actionable survival information.
Which brings us to the final and arguably most consequential section of our deep dive.
Right. We have explored the physics of the threats, the thresholds for sounding the alarm, and the immense engineering required to detect and track these weapons across the globe.
But all of this architecture, the satellites, the phased array radars, the processing hubs, it is ultimately useless if the military does not physically react to the information.
The doctrine draws a very sharp distinction between missile warning and missile defense.
It is a critical conceptual boundary. Missile warning is inherently passive and informational. It is the act of observing, calculating, and reporting.
While missile defense is active and kinetic, it is the physical intervention meant to mitigate or stop the incoming threat.
The fundamental rule established by the doctrine is that warning is the absolute prerequisite for defense. You cannot shoot down or hide from a weapon you do not know is coming.
The application of warning data manifests in two forms of defense, passive and active.
Let's look at passive first. Passive defense relies entirely on the time bought by the early warning architecture.
When the Joint Tactical Ground Station pushes an alert to a forward operating base, passive defense is what the personnel do to survive the inevitable impact.
The warning allows base commanders to sound the sirens. It provides the crucial minutes or seconds needed to evacuate targeted structures, move personnel into fortified concrete bunkers, or equip chemical and biological protective gear if the trajectory and intelligence suggest a non-conventional payload.
But passive defense does not alter the flight path of the missile.
No, the weapon will still strike the Earth. The goal is to drastically reduce the lethality of that strike by hardening the target and removing personnel from the blast radius.
But the doctrine also details active defense, which is where warning data is directly integrated into weapon systems designed to physically destroy the incoming threat.
Right. Active defense feeds the tracking data directly to interceptor platforms.
The doctrine uses the Patriot system as a prime example of theater-level active defense.
It is tempting to think of an interceptor system like Patriot as a standalone shield that simply looks up and shoots down anything that enters its airspace.
But the reality of physics makes that impossible, doesn't it?
Absolutely impossible. A Patriot battery cannot continuously scan the entire volume of the sky above it with enough precision to catch a missile dropping out of the upper atmosphere at thousands of miles per hour.
So it relies entirely on the broader warning architecture.
Yes. When a space-based sensor detects a launch hundreds of miles away, the network calculates the predicted impact zone.
If that zone is protected by a Patriot battery, the network sends a digital cue directly to the Patriot's command system.
It essentially tells the Patriot's organic, ground-based tracking radar to focus all of its electromagnetic energy on a very specific patch of sky at a very specific millisecond.
The warning network cues the local radar. Instead of scanning blindly, the organic ground-based tracking radar acquires the incoming short-range or medium-range ballistic missile precisely as it enters its terminal phase.
And then the system launches a kinetic interceptor.
The sheer geometric complexity of this intercept is staggering. This is not just shooting a fast-moving plane.
No, you have two objects approaching each other at a combined closure rate of Mach 10 or higher.
The interceptor is not flying to where the incoming missile is. It is flying to a microscopic point in three-dimensional space where the missile will be.
Calculating atmospheric density, wind shear, and micro-adjustments continuously.
And the ground radar has to pump continuous updates to the interceptor in milliseconds to ensure a kinetic collision that obliterates the threat before it reaches the ground.
It is an incredible technological achievement. However, the doctrine introduces a harsh strategic reality regarding active defense.
The text focuses heavily on a concept called left-of-launch operations.
This concept is born from the grim economic and mathematical realities of missile warfare.
Because an advanced interceptor missile is an incredibly complex, highly precise piece of engineering that costs tens of millions of dollars per unit.
Right, but conversely, an adversary can mass-produce basic, unguided, short-range ballistic missiles or drones for a fraction of that cost.
This creates an asymmetrical mathematical problem. The offense always possesses the numerical advantage.
An adversary could simply bankrupt a defense by firing cheap rockets until the defenders run out of expensive interceptors.
If a base have 30 interceptors and the adversary launches 50 cheap missiles simultaneously, 20 of those missiles are going to impact the base, regardless of how perfectly the warning architecture and the radars function.
Exactly. The realization that a purely defensive posture is ultimately a losing strategy is what drives the necessity of left-of-launch operations.
The doctrine points to the historical precedent of the Persian Gulf War in 1991.
Right, the Iraqi military was launching mobile Scud ballistic missiles into Allied territory.
While interceptor batteries were deployed to shoot them down, military planners recognized that intercepting the arrows was not sustainable. They had to destroy the archers.
This initiated the Scud hunt.
The Scud hunt was a massive undertaking. Coalition aircraft flew thousands of sorties over the vast, featureless western Iraqi desert, hunting for mobile missile launchers that could pull out of a highway culvert, fire a missile, and hide again within minutes.
It really highlighted the immense difficulty of finding these systems before they launch.
Distinguishing a missile erector from a commercial fuel truck on a grainy synthetic aperture radar screen during a sandstorm proved incredibly difficult.
The challenges of the Scud hunt cemented the doctrine we see today. Left-of-launch operations mean utilizing intelligence, surveillance, reconnaissance, and strike capabilities to find and destroy the adversary's missiles on the ground before the booster ever ignites.
A perfectly functioning warning architecture does not just cue defensive interceptors. It provides the immediate, precise, geographic launch coordinates to the offensive strike network.
Yes. The early warning satellite detects the thermal bloom. It instantly registers the launch origin point.
While the interceptors prepare to shoot down the incoming missile, the warning network simultaneously hands those coordinates to an airborne strike fighter.
The fighter races to the launch origin to destroy the mobile launcher before the adversary crew can reload for a second volley.
So the ultimate defense against a massive missile barrage is an aggressive offense, enabled and directed by the space-based warning architecture.
Exactly. The warning data closes the kill chain. It transitions the military from attempting to catch an infinite number of bullets to actively neutralizing the weapon firing them.
We have journeyed through an immense landscape of physics, engineering, and military strategy today.
We really have.
We began by establishing the mechanical differences in the threats. The predictable, unpowered, parabolic arch of a ballistic missile versus the atmospheric skipping of a hypersonic glide vehicle, and the orbital unpredictability of a fractional orbital bombardment system.
We examined how those physical realities shape the doctrinal rules of engagement.
We explored the rigid demands of strategic missile warning, where the absolute requirement for dual phenomenology prevents a single sensor glitch, like the reflection of sunlight off a cloud, from triggering an accidental nuclear exchange.
And we contrasted that with the survival-driven rules of theater missile warning, where deployed forces rely on instant assured warning, accepting the disruption of false alarms because the flight times are too short to wait for secondary confirmation.
We analyzed the intricate tandem architecture that actually sees the threats.
The persistent stare of space-based infrared sensors operating in geosynchronous and highly elliptical orbits, capturing the intense thermal bloom of the boost phase.
And the critical handoff to the massive terrestrial-based phased array radars using electronically steered electromagnetic beams to track the cold metal body of the missile coasting through the vacuum of space.
And we concluded by tracking how that warning data flows through processing nodes like the Joint Tactical Ground Station to enable survival.
It provides the time for passive defense evacuations. It cues the organic radars of active defense interceptors to achieve kinetic kills. And it supplies the precise launch origin coordinates necessary for left-of-launch offensive strikes to destroy the adversary's capacity to fire again.
It is a staggering testament to human ingenuity. The ability to monitor the entire surface of the planet, calculate the trajectory of an object moving at Mach 20, and physically intersect it in midair is a triumph of physics and processing power.
But as we look toward the horizon of this technology, what is the concept we should be analyzing next? What does the evolution of these systems suggest about the future?
Well, if we look closely at the trajectory of hypersonic weapons and fractional orbital systems, the most alarming trend is the violent compression of time.
Right. Because these systems are purposefully designed to blur the lines between the atmosphere and space, to maneuver unpredictably, and to drastically reduce the window between detection and impact.
During the Cold War, early warning systems provided roughly 30 minutes to analyze a launch, verify the data through dual phenomenology, and brief the President of the United States.
30 minutes is a lifetime compared to the flight times we're looking at now.
With a hypersonic glide vehicle launched from a submarine or an orbital platform dropping its payload, the warning timeline shrinks from 30 minutes to single-digit minutes or even seconds.
And that shrinking timeline forces a profound question about the future of command and control.
It does. The entire architecture we discussed today relies on automated systems feeding data to human beings who then make the ultimate decision to sound an alarm, launch an interceptor, or initiate a retaliatory strike.
But if the time from detection to impact is less time than it takes to physically brief a commander, will human beings soon be too slow to remain in the decision-making loop?
Will the future of missile warning and missile defense require handing the keys of the architecture entirely over to artificial intelligence?
If an algorithmic system detects a hypersonic threat with a 2-minute time to impact, it would have to independently verify the track, calculate the intercept geometry, and launch the defensive weapons before a human operator even fully registered the alarm on the screen.
Entrusting the launch of kinetic weapons, or potentially strategic retaliation, to an automated algorithm fundamentally alters the nature of warfare.
It removes the human capacity for hesitation, intuition, and context.
The very human traits that allowed Stanislav Petrov to recognize a false alarm and prevent a nuclear war in 1983.
As the weapons get faster, the pressure to automate the response becomes mathematically unavoidable. What that means for the stability of global security is the defining strategic question of the next decade.
Definitely something to keep in mind.
The invisible shield we rely on is becoming faster, more complex, and increasingly automated. The diagnostic landscape of the sky is a terrifyingly complex, high-wire act of physics and computation, and the margin for error is continually shrinking. Thank you for joining us on this deep dive into military doctrine.
It's been a great discussion.
Keep looking up, keep learning, and keep questioning the invisible systems that operate silently above you. We will catch you on the next deep dive.